Okay, good morning, good afternoon, everyone. Thank you for joining the IEEE EMBS webinar series on the frontiers of biomedical imaging and analysis. My name is Ping-Kun Yan. I'm an associate professor of biomedical engineering at the Rensselaer Polytechnic Institute. I'm co-hosting this webinar with the doctors Hamed Koskan, Marlene De Bruni, Marius Ingraju. We are all part of the IEEE BIP Technical Committee. So today I'm joined by a special guest panelist, Professor Ji Wang, also from Rensselaer Polytechnic Institute. Professor Wang is well known for his pioneering work on the CT image reconstruction and the innovations of AI in CT imaging. Our guest speaker today is Professor Zhang Chu Ye. Dr. Ye is a professor at the Kim Jong J. Chul Graduate School of AI at Career Advanced Institute of Science and Technology, acronym KAIST. He is also an adjunct professor at the Department of Biomedical and Brain Engineering and the Department of Mathematical Science at KAIST. So he received a Bachelor of Science and a Master degrees from Seoul National University, Korea, and a PhD from Purdue University. Before joining KAIST, he worked at Philips Research. We actually just talked about that because we both worked for Philips Research before. And also later on, he joined GE Global Research in New York. Actually, Niskona is very close to RPI. He has served as an associate editor of IEEE transaction image processing and editorial board member of magnetic resonance in medicine. He's currently associate editor of IEEE TMI and senior editor of IEEE Signal Processing magazine. So Professor Ye has made a number of contributions to IEEE EMBS, and with his dedicated services, he's an IEEE fellow, was a chair of IEEE SPS Computational Imaging TC, and the distinguished lecturer of IEEE EMBS. He was a general co-chair for IEEE ASB 2020. His research interest is in machine learning for biomedical imaging and computer vision. So today he will speak about his research on accelerating conditional diffusion models for inverse problems through a stochastic contraction. Without further ado, let's welcome our speaker.
Okay, thank you very much for the kind introduction. And let me share my screen, 1 second. So now you can see the screen, right?
Right.
Screen.
Hmm.
Okay. Okay, so yeah, thank you very much. And it's a really great honor to be here to present our work. So this is a joint work with my students, Hyungjin Chung. This work is actually appears in the 2 papers. So we actually are summarizing this work as well. Perhaps you may have heard about this so-called diffusion-based generative model. Nowadays, the diffusion model has become a very important part of the generative model for machine learning researches. For example, here, this is actually the state-of-the-art GAN type approaches, which is called the StyleGAN version 2 with adaptive data augmentation. And now the second one is so-called the DDPM, and the third one is the reverse stochastic diffusion equation. Now you can see that image generated from these 2 approaches is as good as StyleGAN version 2, or even better sometimes. In fact, the diffusion model we are talking about is the second and the third approaches. And now our goal is to demonstrate this is can be useful for the medical and other inverse problem applications. In fact, the idea of the diffusion model, especially the score-based generative model, so the stochastic differential equation is coming from Ford and reverse SDE. The idea is following. Now, let's see, starting with this kind of clean image X over here. Now, for the stochastic differential equation is basically adding the noises using the Ford differential equation, stochastic SDE. Now, then for given this Ford SDE, there is so-called the reverse SDE. This is paired. Now, from here in the noise images, if you actually run the reverse SDE, then you can actually recover the images. The image from here and here is not exactly the same because there is a stochastic noise term here. However, they coincide in the distribution-wise. They lies in the same distribution. Another important thing here is now there's a new kinds of term here, which is so-called the score function. We'll talk about this one in more detail later. And based on these approaches, there is so-called the score matching with the Langevin Dynamics algorithm. This is a discrete version of a SD approaches. Here, the idea is following. Now, we starting with the noise sample. This is a false sample. G is a noise, and X is a clean image. Now, Lieber's Langevin Dynamics is actually following this kind of difference equation. This is actually a discretized version of the Lieber's stochastic differential equation. And now here, the term here is so-called the score function, which is actually trained in such a way. We talk about this one later. Listen to it, there is another type of model, which is nothing but the looks very different from the stochastic differential equation. This is so-called the DDPM, or diffusion denoising probabilistic model. This is actually coming from the Markov chain. For example, we have clean images like this, and each step of the Markov chain is gradually adding noises. This process is actually can be summarized like this kind of discrete procedure. Now, the reverse diffusion is now basically recovering from here to the original image using the transition distributions, and this is given in this kind of form. Here, S theta is again trained using some kinds of functions like this. Okay, now it looks like a different. The first one is continuous version of the stochastic differential equation, and this is a totally different Markov chain. But listen, results demonstrate these two approaches are equivalent. For example, here both of approaches are starting with some kinds of function minimization, and here, even though the cost function looks a little bit different, this is basically the same thing. But now you're starting with the noise measurement, and now you gradually improve the result. This is a conditional generative model. In that case, is from the complete noises, we can generate all kinds of images. And now conditional diffusion cases, which is used for the inverse problem, our goal is to generate the images that satisfy the measurement constraint. In fact, these two approaches has a close relationship because this is basically the discretized version of a stochastic differential equation. Now, before we talk about that one, we'll actually discuss about the idea, the term called the score function. Score function is basically the gradient of the distribution. Here, for example, let's think about this kind of distribution, data distribution here. Now, in this distribution, this is a two-dimensional distribution. We have a peak point here and another peak here. Now, the score function is basically the gradient of this distribution. So if you actually follow the gradient direction, you can reach the peak of the distribution. This is what score function is doing. So in order to estimate the score function, people often use so-called score matching algorithm. The idea is following. Now we have a discrete sample out of this continuous distribution. And for example, let's think about this as a phase distribution. In that case, we have each sample corresponds to the realization of the phase samples, as you can see here. The goal of the score matching is from this kinds of discrete sample, our goal is to estimate the direction that pointing out the peak point here. This is so-called the score matching. But the problem is, now score matching algorithm has actually the fundamental issues. For example, let's think about this kind of peak point. If you think about the data samples, mostly it's focused on this kind of peak point here. So if you want to estimate the directional gradient, the area, this red area is more like inaccurate because we have a very few samples. But this green area is more accurate because we have a much more samples. So the goal is from this kind of data scores, our goal is to estimate the gradient flow along all the sample directions. Okay, so there is basically the way to estimate the score function, which is so-called the denoising score matching algorithm. Here, the idea is we are now perturbing the distribution a little bit, And then you can actually see this distribution become a little bit more blurry. So you can actually have more samples around here. And if you think about the blurring in the distribution sense, that means basically adding the noises in the sample space. So that means by adding the noises, you can actually blur the distribution. And from that, if you sample from that time, you can actually access some of the data here. And from the data, you can actually estimate the gradient direction. This is the basic idea of the score matching algorithm. Okay, so now there is a lot of different way of estimating the score function. So for example, the direct way of estimating the score function is we have some kinds of neural network S theta, which is trying to match the gradient directly here. So the goal is to estimate the neural network parameter such that you can actually approximate this kinds of measurement, score measurement from the sample. But the problem is now this kind of score, the score measurement is very difficult to obtain, as we discussed before. So instead of directly estimating this score function, people often use the denoising score matching algorithm. Denoising score matching is instead of sampling this, we are estimating this score function. We are basically estimating the conditional score like this. So for a given clean images, we actually have a noise version of samples here. And now this, we are trying to fit this data. This is so-called the denoising score matching algorithm. The reason I'm focusing on this one is a little bit in more detail is because, for example, if you go back to the original algorithm here in this two equation, there is this kind of part which estimate the transition, which estimate the function here. And so here, there's also a cost function which estimate this kind of S theta function here. Now, these two functions from two algorithms, DDPM, and also this Langevin Dynamics is basically equivalent. That's actually the reason I'm trying to give you some of the background about this kind of score functions. So indeed, for example, based on this kind of denoising score matching cost function here, now for the case of the SLMMD, now you can actually show that this, if you utilize this kind of forward noising process and utilizing, you can actually obtain the gradient conditional probability density function and calculate the score function, you end up with this kind of closed form expression. So that's why you end up with this kind of cost function, which is used to the SLMD. So indeed, this score matching Langevin Dynamics is basically estimating the score function using the denoising score matching algorithm and using these functions and during the reverse diffusion process, during the Langevin dynamics and estimate the clean image. That's actually the main idea. On the other hand, the score matching function for the DDPM is a little bit different because actually the forward diffusion part of the DDPM is given a little bit different compared to this SMMD. Here the idea is following. We have a scaled version of the clean image and the scaled version of the noises. So if we put this one to this log function, you end up with this kind of cost functions. So this is actually the idea of the score matching we are using for the DPM. So in summary, let's get back here again. So in summary, the basic idea of DDPM or SGM, the score matching, the Langevin dynamics, is basically you start to estimate the score function first. And now here, in order to estimate the score function, you are basically the X0 is the clean images we are using. And then you perturb with this one with the adding noises. This is basically the forward diffusion part. And you are adding various levels of the noises. And from here, you are estimating the noise component at each iteration to remove it. So once you estimate this one, during the iteration, you can actually, for each iteration, you can estimate the noise component. And from the noise component, you remove the noise gradually, and finally you can actually you can generate these kinds of images. Same thing happened in SGM. Only difference is how to actually define the forward diffusion and the corresponding the reverse diffusion. Okay, now so far this idea is basically the image generative model, like a GAN or some kinds of unconditional image generation. Now the main part of my talk here is about the conditional diffusion model, which is used for the inverse problem, because this has many important applications in the medical domain. For example, let's think about this kind of inverse problem we are trying to solve. We have a Y measurement. Let's think about this is MR, compressed sensing MR problem. Then Y is a case-based data, which is subsampled. And A is a Fourier transform, which is subsampled version of the Fourier transform. And X is a clean imaging. In the conventional inverse problem, we are directly minimizing this cost function with respect to some kind of constant or regularization term. Now, however, in order to solve this problem using the diffusion algorithm, we actually use two-step approaches recursively. The first step is reverse diffusion step. Now here, this is a score function again. We are basically adding the noises, and this noise level is decreasing for each iteration. So this is basically slowly removing the noises, starting from very noisy images here. Now it is followed with the data consistency, which is basically minimizing this term. This is a gradient step of this one. So you are basically starting from the noise and then doing the one-step denoising and adding the data consistency sum, and then gradually remove the noise and adding the data consistency sum. By automating this kind of denoising and data consistency, you end up with this kind of clean images. This is the main idea of score-based formula for the inverse problem, or diffusion-based formula for the inverse problem, because this is two same approaches. Okay? Now, the reason I'm so excited about this kind of diffusion-based model for the inverse problem is it provides a state-of-the-art performance. Now here, this is a subsampling mask in the case-based data. If you actually think about the total variation, the compressed sensing approach, which is recovered from here, you can clearly see there is a smoothed version of the reconstruction, as you can hear, compared to the ground truth imaging. Okay? Now, if you actually think about the one-dimensional subsampling, still remaining aliasing artifact, you can see here. If you use a unit-based approach directly from here, it's much better, but still there is some of the areas remaining artifact because there is so much subsample. This is the state-of-the-art supervised learning approach, so-called the Doodle NAD, which won the fast MRI challenge. But it's better than this, but still you can actually see the structure here is blurry. Now this is a score-based approaches. So now you can clearly see that with exactly the same data set, you can actually have much more details compared to all other approaches. So we can clearly see that score-based approach is much more efficient. And furthermore, another important thing here is now this has an excellent generalization capability. Because now score, all you need to estimate is basically the score function with respect to all kinds of noise level. And in these approaches, we basically train our network with the fast MRI data, which is a knee data. We train the neural network using the knee data, but apply for different sampling pattern and different organs, as you can see here. But still, it actually provides very excellent result. And in terms of the signal-to-noise ratio, but also in terms of quality, we have a significant improvement. Same thing happened, trained with the knee data, you can actually apply it to the brain data. We have a much more clean image compared to this. Okay? Furthermore, another very important advantage of this score-based approaches, it can actually provide uncertainty map as well. Now, this is a ground truth image. Now this is a uniform subsampling pattern with the factor of 2 and factor of 4, 6, and 8. If we just do the inverse problem, you can actually see this kind of aliasing artifact. Now the second law is a reconstruction using the score-based diffusion model. Now you can clearly see that from this sample, we have a much more clean images, and which looks very similar to the original image. However, because our method is stochastic, because actually in the iteration step, there's always a noise term added together. So that means if you're starting with the different kinds of noises and adding different noises, we have a different realization of the reconstruction. So from that on, we can actually calculate the variance of the reconstruction. Now you can clearly see that at the smaller downsampling factors, this basically the noise is uniform. But if you have a large acceleration factors, most of the noises, uncertainties are concentrated along the edge images or the knee part, the joint part, as you can see here. This gives a map to the doctors where which part is not accurate in this kind of reconstruction. However, in spite of this kind of nice property of the score-based diffusion model for the inverse problem, there's a very important downside. The problem is it's very, very slow because we are starting from the noise image, complete Gaussian noise, and gradually remove the noises, and you end up with the clean image. So this is a PSNF value for the MRI problem. Now we have a 2000 iteration. Yeah, 2000. For example, if you think about the fifth-fold neural network, UNet is just like one iteration. This is 2000 times slow. Now, if you have this kind of thing, and if you actually reduce like around 200, then that's still okay, but there is a slight increase in noises. But if you actually further reduce the iteration number of steps, you have a significantly reduced the performance. So this is the main drawback of this diffusion mode, and people are interested in finding a way to accelerate this problem. In fact, this paper, which will appear in the CPR this year, is actually provide the solution for the acceleration for the case of the inverse problem. This is what they call the CCDF. This is a slogan with the Come-Closer-Diffuse-Faster. You can actually understand why we have this kind of slogan. Now, in order to understand this one, let's go back to the original version of the score-based approaches for the inverse problem. Now, this is the inverse problem for the super resolution imaging. This is our measurement, which is subsampled measurement, and our goal is to recover these images. Now, in the existing score-based approach, we start with the noises, and each iteration we are imposing the data consistency sum for this measurement. And you gradually remove the noises by adding them together. Finally, you end up with this clean image. Now, the question is, if you think about this step here, basically this is noise here, right? So the question is this part is really necessary? So the question is, instead of doing that, you start to see some of the face images from here in the wave faces here. So maybe skipping this, and suppose we start from here, then what happened? So the idea is as following. So now you have a measurement which is subsampled images. Now you are because of that, this is actually upsampled images. So this is very blocky like this. Now you are basically adding the noises here. Now if you add the noises, you can actually see this kind of Gaussian noise pattern here. Now let's think about the ground truth imaging. Add the noises, we actually have looks like this Gaussian noises. Now, the difference between these two and the difference between these two, of course, the difference between these two is bigger because you are also adding noises. However, these look similar. So the question is, now, we actually have the noises different here, but if you actually have a way to actually denoise the image very quickly, then the question is, if you reconstructed it, there's a way that the recovered image from here, starting from here, is smaller than the initial realization. In fact, that means the idea of this one is you start with this initialization and then adding the noises, and starting from here, you are gradually removing the noise by adding this kinds of constraint. That's the basic idea of CCDF. In terms of algorithm, this is given by this. First, adding the noises here, and then we are following the iterative denoising but we have a denoising step and data consistent step. But the important part is now adding noises is starting from the initial guess here. And then we are now slowly denoising the noises by imposing the data consistent step. Okay, before I talk about the basic understanding, we actually see the intuition first here. Now the idea is now we actually starting, if we just vaguely starting from the random noises, now you can actually gradually remove the noise here. But it turns out the decrease of the noise value during the diffusion process follows some kind of exponential decay. That's actually the key point. Which means that now if actually starting from here, now adding noises is for diffusion step is increasing the estimation error, but however the increase is controllable. It's basically linear or controllable. But what I can show you mathematically is now the denoising process is removing the noises errors exponentially fast. So even though in adding noises is increasing the noises, but the same step size, the denoising can remove the noise quickly, which means compared to the original images, the number of steps required to achieve this image is much smaller. Based on this idea, we can actually further show this. If instead of starting from this version of the noises, if you have a better estimation, whatever means we have a better initialization, then this error is smaller, so you can actually add smaller number of noises here, and then remove the noises in an exponential way. Then you can actually have a much quicker number of iteration steps. It's much quicker compared to this, and even compared to this one. That's basically the idea. So the question is, then it's really the case. So that means when the error increases by adding the process and the removing during the reverse process, whether this is really the decaying in an exponentially faster way compared to the adding noises. In fact, the paper we actually demonstrate here is actually in the CCDF paper is, in fact, this is really the case. That's actually coming from the idea of so-called the stochastic contraction. So stochastic contraction is coming from the mathematical concept of so-called the contraction mapping. Contraction mapping is as follows. For example, let's think about the function f. Function f is called contracting if actually have differences for the given two input x and y after applying the function. If the distance is smaller than original distance between the input value, this is actually called the contraction mapping, which means the lambda is smaller than 1. And if it is nonlinear function or whatever function, this lambda is directly calculated from the Jacobian term. So if a singular value of the Jacobian is less than 1, this function is called the contracting function. So that means if actually add iterating x and y in the multiple times, and as iteration goes on, the distance becomes smaller and smaller. That's the main idea we are using the contraction in the optimization theory. Okay. Now this is for the deterministic mapping. Now if you see the reverse diffusion process, there is a deterministic function here, and also there is a noise additive term here. For this kind of stochastic iteration, and Fan et al. They demonstrate this is also, we can actually quantify the distances, variance of iterations with respect to initial iterations, which is now decaying down in this term. Now lambda is smaller than 1. So now here, you can see here, as I goes on, this term, the latter term, is now decaying. This latter term is decaying exponentially faster. This is reduced, and there is a constant term here. So which means if you actually choose lambda very carefully, you can actually see that this is most of the diffusion models satisfy those kind of things. But if you actually choose the lambda, then this term becomes smaller, this term error becomes smaller than original initial guess. So, in fact, what happens is, in this paper, what it demonstrates is, in fact, this kind of stochastic differential equation and the reverse diffusion is basically the contracting. So let's think about the SMLD, score matching Langevin dynamics. Here, the forward diffusion is given in this way, and the reverse diffusion is given in this way. This is a deterministic term, and there is a stochastic term here. Now, if you calculate the Jacobian of this deterministic term and calculate the singular values, you can actually show this value is given in this way. Now, furthermore, in the original score matching Langevin dynamics, this sigma is increasing function. Sigma is actually exponentially increasing, so the ratio between the two is always less than 1. So that means this reverse SD is stochastic contracting. We can actually further show that if actually there is a data consistency term here, still by incorporating the data consistency together, we can also show that this error from the reverse diffusion is also contracting compared to the initial value. In fact, what I can show you is this kinds of lambda value and this value has a very close form expression. For example, DDPM or score matching Langevin dynamics, and there is also a very popular approach which people call the DDIM. Everything we have a closed form expression for this contracting factor, and we can also further show that current scheduling of the noise sigma value is always satisfying this term is less than 1. So which means this error for the initial value after the forward diffusion, and this is a reconstruction error after the reverse diffusion, is always satisfying this kind of equations. And because lambda is now less than 1, we can actually show the very, very important theoretical finding here. This is so-called the shortcut test, which means that now this epsilon 0 is actually the difference from the ground truth, errors from the ground truth to the initialization. Now this epsilon bar is after the reverse diffusion from the initial value and adding noise and the reverse diffusion, then this is actually can be controllable with respect to mu parameter. There is always number of steps you can find with respect to mu such that this can be reduced to compare to this. Furthermore, what I can show you is this epsilon 0 is getting smaller, which means that your initialization is better, then you can always reduce the number of step size. This is what it says here. Now, in this case, if you're starting from the 0 initialization, our initial epsilon n value, initial error is basically the noise component like this. So number of diffusion to reduce is quite significant. Reverse diffusion is quite significant. Now, if you actually have a initial value initialization like this, then difference between this one and the ground truth is about this. Now, one step diffusion, you can actually find the number of diffusion steps to reduce this one smaller than original errors. Furthermore, if you have a better initialization, then the number of steps you can actually reduce to the certain level is much smaller than compared to this one. So that means you have an initialization which is closer to the ground truth images, whatever means, then you can actually have a much faster diffusion. So the question is how to make this initialization better. In fact, there is actually the why we can actually there is actually the room to actually incorporate the conventional approaches, which means now usually, for example, in this kind of inverse problem, there is a lot of existing neural network approaches. For example, in the MRI cases, there is a unit time approaches, and same thing in the super resolution approaches, there is a various kind of spot resolution fit for neural network, just one step. So you apply that one, and starting from here, and you add noises and remove the noise, you can actually have a much better images compared to the original CNN-based approaches. That's the main idea. This is some of the result we demonstrated in this paper. Now, this is the input image with the 4x downsampling compared to 4x subsampling compared to the ground truth image. And this is 8 times subsampling from the ground truth image. And this is a 16 times subsampling compared to the ground truth image. Now, this is a ESR GAN is actually the state-of-the-art supervised learning approaches. From here, if you train in this 4 times subsampling and the paired mapping, you can actually have this kinds of reconstruction like this. But if you actually have a matching images from here to here, then you can actually see the reconstruction is become a little blurry. And if you actually train with the 16 times subsampling in these images, your reconstruction is very, very blurry, as you can see here. Okay? Now, here, this is SR3 is actually latest recent version of the diffusion model, original diffusion model, which was actually proposed by Google engineers. In that case, they require thousands of iterations. But if you just apply 20 steps of diffusion, you can actually have from images, you have a recovery, but however, we have a lot of noises. And even in this 6 times accelerations, then subsampling, you don't see any kinds of images. This is another state-of-the-art diffusion model people has proposed for the conditional diffusion model. This is better than SR3, but however, still the reconstruction is not good. Now, in the rightmost column is our method. We're just using the 20 times step diffusion, starting from the ESC GAN and adding the noises and the 20 times diffusion. We have much more clean image compared to the ESR GAN. And for example, in the 8 times subsampling, you can clearly, and even in the 6 times subsampling, you can clearly see this kind of fall of the animal, but you don't see any kind of thing here. So using only 20 step iteration from this image, you can actually have this images. Furthermore, another important thing here is this is not a supervised training at all. Our diffusion model is only trained with the clean images only, without any kinds of paired mapping. So it can be actually utilized for the 4 times subsampling, 8 times subsampling, and 6 times subsampling without any problem. But in the supervised learning, you need actually the separate training mode. Now, same thing here. This is an inpainting problem. In the inpainting problem, input image is like this, and the ground truth image is like this. The goal is you are basically estimating this part and estimating this part from the neural network after training. Now, this is a GAN-based approach, one of the state-of-the-art GAN-based approaches. In that cases, we are now trained this GAN model, and from here you feed in this data. Now, compared to the ground truth images, you may notice that there is the beard part is missing and the teeth is not clear. And same thing here, the teeth is not clear, the eye is not natural compared to the original image. Now, this is a diffusion model, the traditional diffusion model, starting from the complete noise images. After 20 steps of diffusion, as you can see here, there's still remaining noises here. And if you actually think about this images here, now the background of this is noises, but now in the foreground, which is missing part, has a different kind of contrast compared to here. Now, this is a proposed method. You're starting from this approaches, okay? And then adding noises, and then do the only 20-step diffusion, you start to see these kinds of beard. Even though original initialization, you don't see any kinds of beard here. And you don't see any kind of thing here, but now you can start to see the teeth very well, as well as the eye is much more accurate compared to other images, as you can see here. So that means this kind of acceleration using better initialization at the small number for reverse diffusion has much more better reconstruction compared to the older state-of-art approaches, as you can see here. Now, this is MRI reconstruction approaches here. Now, if you see here, this is original unit-based approaches. Now here, this you can clearly see this kind of edge structures is missing compared to the ground truth imaging. Now this is a score-based approaches. As I showed in the before, this is much better compared to the unit time approaches. Now this is based on the acceleration, based on the better initialization. In this case, you're starting from the unit approaches, and then you're starting from the reverse diffusion. Now, you can clearly see that in terms of quantitative value, this is better. And also, if you see the compare side by side, there is actually a little bit of errors in these images, but this is much more accurate compared to the original score-based approaches. Okay? So, in summary, we demonstrate this diffusion model, which is actually coming from the stochastic, which is coming from the Markov chain models, or based on the stochastic differential equation. Most of the approaches are basically equivalent, but this is actually the exciting new path for solving inverse problem. Originally, it was demonstrated for the generative model, like again, to generate the face images or whatever images we are interested in. But now, by adding the conditioning as a data consistent sum, we can actually utilize this diffusion model to solve inverse problem. Furthermore, compared to other supervised learning approaches, in that case, you have a measurement and the clean image pairs, and you can actually need to train that one if actually your data is different. You need to retrain it. But in this case, diffusion approaches is a universal solver. You don't need any kinds of pair data at all. You just have a clean images, which can be actually arbitrary images. For example, in the MR case, you have clean images of the knee, but you train that one, then that can be utilized for all kinds of sampling pattern and all kinds of anatomies as well. Because this diffusion model has a great generalization capability. The reason for that is as following. We have this is iterative approaches. So at each iteration, there is a chance to actually incorporate this data consistent sum. So even though original diffusion model is a little bit different, which is not exactly the same as a data consistent sum, there is a way you can actually correct it. So it actually imposes a great generalizing capability. Furthermore, what it demonstrates here is the reason this kind of reverse diffusion and this kind of conditioning based on data consistency generate a good image is because it satisfies the stochastic contraction conditions. So the error after it can be reduced much quickly compared to the full diffusion. So that's why you end up with the much clean images, whose error is smaller than the full diffusion part. Okay? With that, I'd like to conclude my talk, and thank you very much for your attention.
Thank you very much, John, for your very exciting talk. Very impressive results. I'll actually hand it over to my colleague, Professor Jung, for handling the question answering.
Actually, let's just push this wrong button. So just get a question from audience. So any questions you can type in the question and answer box.
So maybe I can start a quick question that, well, some of your work actually to appear like a CVPR is not there yet. So if the people interested in your work, where can they actually find the publication? Do you have the preprint already?
Yeah. So we have two papers here. This acceleration scheme, CCDF, is a CVPR. You can actually find, you can actually search my name and then this title. If you search this title, acceleration diffusion, and also the this motto here, this come closer and diffuse faster. then you can actually find the paper in the archive very easily. And also, this original part, score-based diffusion model for accelerated MRI, is already accepted. This is appears in the media. This will be appearing in media, but it's available in the archive as well. So you can find the score-based diffusion model for accelerated MRI, and you can actually find the paper as well.
Great, thanks.
Jung, you mentioned greater generalizability. That's a wonderful work. Would you make some comments on stability, say adversary sample related performance?
Okay, that's very important question. But I think that's actually, in terms of the stabilities, I believe this diffusion model has a better chance compared to other CNN-based approaches. The reason is as following. Now here, basically there is two steps. One is a denoising step. This is coming from the neural network. Okay? So if a neural network is unstable, maybe there is some way that this can be diverted a little bit. And also there is error term adding here. So error is already adding. That actually also improves the robustness as well. Now, once this one is done, now it is actually corrected with the data consistent term. So whatever values we are generating, it should actually project it to the data consistent term. So by doing that, you can correct it. So because of that, I believe this is much more stable compared to just like a fit-for neural network approach, which just have a one open loop, one step from the input to the output. In that case, there is no way to correct it.
Yeah, I see your point. Also, your fast algorithm. So I understand your fast algorithm, you have one step forward, you get a better estimation. So my question, when you do the one step forward, will that affect the target distribution?
Pardon me?
So if you do this one step forward process, then you do reverse. So your outcome will follow a data distribution. Do you think if you do this fast, you call it Come-Closer-Diffuse-Faster, you do this, then you end up with your synthetic image. Then the images will follow certain distribution. Will the distribution the same as our original diffusion model generated images?
Yeah, that's a very, very important question. And yeah, that is true. Now, one step diffusion, this image distribution become Gaussian. Okay, this signal is Gaussian. Now, what happens is in the reverse diffusion, is actually we are basically utilizing. We actually mentioned this kind of error. Error is reduced. This error between the two samples is reduced. Expectation, the average error is reduced. Now, utilizing this kind of thing, you can generalize this one. Instead of having the expected errors, you can actually derive the very, very similar form using the Gaussian distances as well. Gaussian distance is basically the distribution statistical distance between the distribution. So which means that the statistical distance is also decreasing. So that means starting from the Gaussian distribution, but we are now after the reverse diffusion, the final result, the distribution of the final result, the statistical distance of the final result to the ground truth is also decreasing as well, exponentially fast.
Okay, I think that's all my questions. So any other questions from audience? Jung, would you please comment a little bit more? You mentioned the computational time. Would you compare this approach versus competing approach in terms of computational time, training time, inference time?
Okay, so if you want to actually use a 2,000 iteration or 1,000 iteration for ML reconstruction. In that case, in terms of computation time, is several minutes. So it's not good for the real application. Okay. However, with this kind of acceleration scheme we demonstrate here, like a CCDF, we actually implement this one for the real scanner MR, and that's actually being tested in the clinics right nowadays. It's like one slice reconstruction is like a 2 or 3 seconds. Okay. Yeah, still the doctors that's okay said that's okay, but of course actually it's better if you actually have a sub-second reconstruction. That's better. But if you think about this, is a 20-step iteration using the neural network. So it's always, for example, 20 times slower compared to just like unit type approaches, because unit is just like applying one time. But you still need actually iteration here. They're slow, but still by actually utilizing this one with the fast computers and acceleration scheme, there's a way you can actually utilize this one in the clinical environment as well.
So yeah, this actually the results are very impressive. But initially, the idea kind of counterintuitive, right? In order to like get a better image, you kind of reverse a little bit. So how did you actually start looking into this approach, and what was the inspiration there?
Okay, so in fact, actually, there's actually there's just like adding noises and then removing it. Yeah, that's actually this kind of thing is empirically found from my student Hyungjin. He actually show that if you're just starting from this clean imaging, it's not possible to actually arrive at, because the basic idea of diffusion model need to be starting from the noise images. So it's better starting from the noises, but instead of completely adding noises, we just slightly add noises and remove it. That's better. And however, this kind of idea was actually originally proposed for a so-called idea of SD edit. In that case, it's not for the inverse problem. For example, if you want to actually edit some of the part of the original image, in that case, you just black it out. You have remove some part, or maybe this is just like a mask image, like a segmentation image. You're adding the noises and then make this one as like a photorealistic image. That kind of idea was used originally for the generative model, not for this inverse problem. So yeah, there is some kinds of inspiration from those kinds of existing approaches. But however, this kind of theoretical analysis as well as application to the inverse problem is our own contribution.
It's cool, very cool. Thank you.
Mm-hmm.
So it seems actually that's all our questions. Yeah, the audience said actually thanks for presenting the interesting work. Thank you.
Great, thank you.
All right, with that, we can conclude the webinar today. Thank you very much, everyone, for attending. Thank you, our speaker, for giving this exciting talk. Thank
you so much. Yeah.
Thank you.
Thank you very much for invitation.
Okay.
Yeah.
All right,
Bye-bye.
take care. Bye.